Hello guys, welcome to Fire Racer Workshop, and in today's video we're gonna be simulating the full bridge rectifier on Multisim. Now before this experiment, I have already performed two more experiments on Multisim, that is the common base configuration of BTECH, and I've also performed the center tap rectifier on Multisim, so you can check those videos out by clicking on the pop-up I button. Secondly, I have just covered all the experiments in your BTECH second semester on OrCAD as well as on Tinkercad, so do check out those videos by the playlist that's linked in the description down below, or click on the pop-up I button to watch those videos. So those are just really dope videos, and I've just covered each and everything in those videos, and the BTECH second semester syllabus for electronic device has been finished in those videos. But however, I'm just gonna do it for Multisim as well, so stay tuned for those videos. So I'm gonna be covering each and every experiment in your BTECH second semester electronic device on Multisim as well, in a similar way like I did for the OrCAD as well as for the Tinkercad. So on your screen right now you can see the circuit that we are going to be simulating today, and right now on your screen you can see the simulation results for that circuit. Now without further ado, let's get started and let's open up Multisim. Let's just give it some time to load up. Over here we can just see a beautiful Multisim page. Not beautiful, by the way, whatever. Anyways, so first of all we are gonna go to place and we're gonna go to components. First of all, we will be needing a transformer for this particular experiment, so let's just import a single phase, one primary and one secondary winding transformer. So there's a transformer that you're gonna be needing. For the center depth rectifier, you need a one primary winding and two secondary winding type of transformer, but for this particular experiment you're gonna need one primary, one secondary winding, the normal transformer that's available. So let's just drop it in. We're gonna also need a power source, so let's go to power source and select on the AC power. So it's just gonna give you the AC power, it's just gonna give you a 120 volts RMS and 60 Hz sine wave. So that's the normal city frequency that you get on your outlet. So however, you can also change that if you want to, but that's just that's just fine. For me it's just fine. So then we're gonna go to the diodes. So let's just go to the section for the diodes, and right here these are the diodes, and we're gonna go with the diodes, normal diodes right here. Just select on this section. Now we're gonna type in 1N4007. So this is the diode that we're gonna be using for this experiment. So we need 4 of these diodes for the full bridge rectifier. So this is called full wave rectifier as well. So we're gonna need 4 of these diodes, and you can also use like any of the 1N400X series diodes. So right now on your screen you can see the data sheet for all these diodes. The difference in these diodes is the reverse breakdown voltage of this diode. So for example, for this 1N4007 diodes, the breakdown voltage is about 1.5 kilovolt. So, and secondly, I just love these diodes, so I've been using these diodes since I was in class 6, so I do have a kind of a connection with this diode, so I'm gonna use these diodes regardless. So we're gonna place one diode right here. We need 3 more diodes. Now be careful, just press Ctrl R on your keyboard to rotate the diodes. I'm gonna rotate these 2 diodes. I'm gonna rotate 2 diodes in this orientation. I'm gonna place it right here, right? And we need 1 more diode. That's just gonna be on the normal orientation, like we are placing the top diode right there. We're also gonna need a resistor. So go to basics, and over here you can see there might be a section called resistor. So we're gonna go with a 1K resistor again. We're gonna go with a 1K resistor, Control R to rotate it, and we're gonna place it right here, and then we are all done. And you also need, by the way, a ground, so we're gonna also take the ground as well, while we are on it. So let's just take the ground and let's just drop it right here. Let's just wire up everything now. Now for this particular experiment, you can't just take the readings at the output of this transformer, because there has to be, like, you have to make a differential measurements to take those to take that reading. But I'm not gonna go in differential measurements right now, so we'll be taking the output, we're gonna be taking the input reading at the 120 volts 60 Hz RMS voltage source. So you have to ground this particular thing. So let's just wire this up. First of all, I'm just gonna wire up everything, and this is how it's just gonna be wired. So these 2 diodes, please just make the connections like I'm doing right now in this video, otherwise you're just gonna mess up. I don't want anybody to mess up in this circuit. And right here, this is how the connections are going to be made. And we can also just drag this wire a bit to that side. We need 2 more grounds like this, so I'm just going to copy paste this ground, one for here and one for over here. So we need 2 more grounds, so let's just wire up these grounds as well. And I'm going to connect this ground to right here. Now this resistor is going to be wired up right here, and this ground is going to be connected to this resistor, and our circuit is complete. Now if you need, you can just change the primary to secondary ratio of this transformer, but it's just okay for my taste. I need a 10:1 ratio of this transformer. You can also go with a 10:2 ratio or something like that. I mean, you will just get at the output, you'll just get 24 volts RMS if you just go with the 10:2 ratio. Right now I'll be getting 12 volts RMS at the output of the transformer. So let's just import our oscilloscope. Now for this particular experiment, I'm again going to be using a 4-channel oscilloscope, because 4-channel oscilloscope is much easier to wire up than a 2-channel oscilloscope. I'm going to use a 4-channel oscilloscope, and I'm going to be copy pasting the ground again to ground this oscilloscope right here. So this is the ground for the oscilloscope, and on channel number A I'm going to be connecting the input, that is the voltage source right here. So this is going to be our input. So this is going to act as our input for the rectifier, and in channel number B I'm going to be connecting it to the resistor, so that is the output of the rectifier. So we're all done right here. I'm going to change the color of this particular wire as well, so that the trace in the oscilloscope also changes to that color. I'm going to go with the yellow color for this one, and let's just go with a pink color for this one. So it just looks dope. I don't know why. I mean, these kind of color like looks dope on the screen of the oscilloscope. I do have an experience of these kind of things, so I know these actually look dope. So the wiring has been completed. So let's just set up our oscilloscope, or let's just do one thing. First of all, let's just go to simulate and go to your analysis and simulation settings. Now this is completely optional. If you'd like to do it, you may do it. If you don't like to do it, you may not do it. Over here, what we're gonna do is we're gonna adjust the step size of our simulation. What we're gonna do is, like for example, this is the maximum step size of our simulation, so we're gonna adjust it to e into 10 raised to the power minus 6. So what is essentially gonna do is it's just gonna increase the precision of our readings, and you'll see why. I mean, the readings just look really dope after this, like dope as hell. So after you just like change the setting, but yeah, it's just gonna make your simulation a bit more slower, and you'll see the drawbacks as well. But yeah, it's just pretty optional. If you want to do the setting, like if you want to change the setting, it's just up to you. I'm just gonna change the setting. I'm just gonna hit on save. Let's just open up the oscilloscope, and I'm just gonna enlarge the screen of the oscilloscope so you people can see it better. So right here, this is the oscilloscope screen. Let's just simulate a circuit now. Now you see over here what we're getting. So these are just super precise, super duper precise. Okay, now let's just adjust the settings. So in my previous video, so if you haven't checked out the stator trap rectifier, so just do check out that video first, because in that video I just covered all the basics for this particular oscilloscope, so how to operate it and all that stuff. I'm just gonna do it normally right here. Just set the trigger to normal. Alright, and it's just gonna be at the rising edge. Now set all the channels coupling mode to DC. Obviously it's just already at DC. We're gonna, for first of all, the channel number A, it's connected to the input of the rectifier, so that is the 120 volts RMS sine wave source. So we're gonna change the volts per division setting. So if you're just doing this experiment on a real oscilloscope, you're gonna do it beforehand, otherwise you're just gonna blow up your oscilloscope. The amplifier of the oscilloscope is just gonna blow up. So I'm just gonna change it so that it just like fits within the trace. Now you can see it's just like perfectly fitting within the trace. So right here you can see I've just like selected 200 volts per division, I guess 200 volts per division for the scale. So it's just all set. Now let's just move it, let's just scroll it down a bit. I'm just gonna take it up to, let's just say 1. So over here this line is gonna act as a 0 for this particular sine wave. Let's just move on to the output. So for the output, I'm gonna decrease it a bit. I mean, I'm just gonna give it like, I'm just gonna keep it at 10 volts per division. And for the time scale, for the times per division, so it's just okay. So if you need, you can just like decrease the times per division settings so that you just get a more precise graph. Okay, So let's just take the readings at a single shot mode. You can also take the readings at a single shot mode. It's just gonna capture the readings at once, and then once it has captured all the readings, you're just gonna click on stop. Now right here, now we have just stopped our readings, and over here you can see these are the simulation results for this particular experiment. Now, if you'd like to calculate, like for example, what's the peak voltage of the sine wave that you're getting or the output that you're getting, you can easily do it by the use of these triggers and the cursors. So these are the cursors, by the way. So this is the cursor number 1. Okay, so sorry, this is the cursor number 2 and this is the cursor number 1. So what we're gonna do is we're just gonna set the cursor to this pink right here. So this pink waveform, we're gonna set it to the peak of this pink waveform. So this is the maximum amplitude of our output, and second cursor we're gonna set to the peak of this particular waveform. So this is the maximum amplitude of our input waveform. So you can, if you need to include these readings in your file, you can do so, but it's just completely optional. Well, I don't have any idea, but if you want to include these readings, so you may do so. Secondly, for the cursor number 1 is just going to measure the minimum value of the sine wave as well as now the maximum value of the output. So over here you can see all the readouts. So this is for the cursor number 1. So you can see it is at the time of 45.818 millisecond, and at channel number 1 is just detecting a voltage of 169.703 volts, and at channel number B is just detecting a maximum voltage of 15.614 volts. So this is how you're gonna take the measurements. And for trace for the cursor number 2, the T2, so you can see over here it's just detecting a maximum waveform, the maximum voltage as 16.701 volts, and at channel number B is just detecting the maximum voltage as 15.614 volts. So this is how you're gonna just take the readings. Now if you want to see your circuit, how will it look like if you didn't change the parameter for this particular circuit, go to analysis and simulation tab, and let's just uncheck this box and just click on save. And now let's just run our simulation again. So this is how our waveforms are gonna look like, you can see. So this particular waveform, like for example, the points that are being used to plot these waveforms have reduced considerably. That's why you can just see jagged edges on your waveform. So that is, I absolutely hate this kind of waveforms, and I just love to see them as precise as possible. Even on OrCAD as well, I just like tend to take like a lower like I just tend to take much more readings, like as much readings as possible. So therefore, like we just get a much more precise graph. So this is not looking that good, but if you just like change the settings, so your waveforms are just gonna look dope as hell, dude, dope as hell. So that's all for this video, guys. I hope you like this video, and I'm gonna be bringing up the half-wave rectifier pretty soon, so stay tuned for that. And thank you for watching. So smash the like button if you like this video, and do subscribe to my channel. See ya in the next video. Bye bye.